Hello and welcome. My name is Victor Gijsbers and I teach philosophy at Leiden University in the Netherlands. In this series of videos, I want to take a look at David Albert's book, Time and Chance. Time and Chance. And time really is at the center of this book, and specifically the asymmetry of time. The fact, you could say, that the past and the future seem to be wildly different directions. To give just one example of that, we can influence the future, we think, but we don't seem to be able to influence the past. Or to give a very different kind of example, it's easy to break an egg. It is extremely hard to take a broken egg and reassemble it into an egg. And when I say extremely hard, I mean impossible. So the future and the past seem to be different in important respects. And there are several ways in which philosophers can try to think about that. And David Albert is taking an approach that I would call a philosophy of physics approach. So he is going to be taking a long and hard look at certain theories from physics, but not so much as a physicist, but as a philosopher, trying to understand what those theories are really saying and how they interact with the philosophical questions about time that we have. And in particular, the book is going to be not only, but mostly about what we can call the philosophy of thermodynamics and statistical mechanics. So that would be the parts of physics that talk about temperature and heat and, very importantly, entropy. And so we'll be looking at especially that part of physics, although we will also find that a little bit of cosmology pops up and some quantum mechanics near the end of the book. But it's going to be mostly thermodynamics and statistical mechanics. And we'll talk about the difference between those two later on when they become important in the book. Now, one of the things that happens when you write a philosophy of physics book, and certainly when you write a philosophy of, like, let's say, statistical mechanics and thermodynamics book, is that you're gonna have a lot of pictures, some formulas, but also these nice little pictures about pistons and gases and particles and walls and so on and so forth, which can be extremely helpful in understanding what's going on. And there is no way that I'm going to be able to reproduce that or do that for you in a video like this. So it is highly recommended, as really with all the videos I make about books, it is highly recommended to use these videos as an accompaniment to the book. Right, because the book is going to give you a lot of things that my videos can't. In the videos, I will be talking about the most important points that Albert is making. I will maybe be zooming in on some questions or some difficulties or some things where I think I have something to add, either complicating Albert's story or maybe questioning Albert's story, or just explaining things that might be a little bit difficult, a little bit more than Albert does. Although I have to add that the book is fairly accessible, even if you haven't done a lot of physics or a lot of mathematics. I mean, yes, there are some formulas. You need to be able to read that if you want to follow the book, but it doesn't sort of require a huge background in the sciences to follow this book. Now, the first chapter of the book, and the one that this video is going to be about, is a chapter called Time Reversal Invariance. So let's think about that term first. What does it mean? Time reversal invariance. Well, invariance means that something doesn't change. And time reversal is flipping time around, right? So you take time, so to speak, and you switch the past with the future, and then that would be time reversal. And so time reversal invariance is a property that something has if it does not change when you flip past and future. So, take your life, for instance. Your life would look very different if it was switched around in time, right? Because your life is extremely asymmetric in time. You started out as a baby, hopefully you will end up as an old person. A baby and an old person look nothing like the same. They are very different. Flipping your life around in time would make it a very strange, weird thing. Like there would be this old person slowly growing young, but also behaving in absolutely incomprehensible ways, I suppose, because everything is going to go backwards. It's completely different. And so your life is not time reversal invariant, right? It changes, it looks very different when you flip past and future. Now, what is interesting is that although the world is full of such things that are things, processes, whatever, that are not time reversal invariant. So although we see around us all the time stuff that is not time reversal invariant, nevertheless, there seems to be an important sense in which the physical theories that we have are time reversal invariant. So there seems to be an important sense in which physical theories are blind to the difference between past and future. If you take a physical theory and you flip around time, and that could be very easy because you just look where they write a little t, right, the t of time, and you put a minus sign in front of it. If you flip around time by putting a minus sign in front of every t, you'll end up with the same physical theory. And that is, at least at first sight, very mysterious. How can it be that we live in a world where people only grow older and never younger? Where eggs break and don't come together again? Where we can get knowledge of the past in a way that is completely different from how we can get knowledge of the future? Where we can influence the future in a way that we can't influence the past? And so on and so forth. How can all of that time reversal variance, so to speak, all of that stuff that is asymmetric in time, how can that exist if the fundamental laws of nature would seem to be time reversal invariant, right? If they are flippable around in time without any change, and so if the reverse of anything that is happening in the world would fit the laws of nature just as well as what is actually happening fits the laws of nature. That, in essence, is the question that Albert is going to ask in this book. Right? How is it possible that the world is full of stuff that is asymmetric in time, even though the laws of nature are in an important sense symmetric in time, that is, they have time reversal invariance. Now, the main aim of the first chapter, after sort of setting out this problem, is explaining to us in more detail what time reversal invariance is. And one of the strengths of Albert's book is that he sort of really tries to be very clear about everything, think it through in a lot of detail, and sometimes this shows that the sort of more informal way that people have been speaking about things in the literature is misleading or doesn't tell the correct story. And that is what Albert is going to tell us about definitions of time reversal invariance and this claim that physical theories are time reversal invariant. So let's take a look. And Albert starts with Newtonian physics, and in fact a very simple form of Newtonian physics, where basically all you have are point particles. So there are little particles that are sort of infinitely small, and they have masses, and they have positions, and they have speeds, and they are moving around. There are forces that, describe the interaction between these particles. There's Newton's law of motion, Newton's laws of motion, I should say, the most important of which is F is m times a. So a force is equal to the mass times the acceleration. So that tells us what happens when there are forces working on these particles. They are going to be accelerating according to this law. And suppose that the universe is like that, right? There are these particles, they are moving around, there's forces working on them, which means that they are accelerating or decelerating, like they're changing their velocities. And one of the nice things about Newtonian mechanics is that it is completely deterministic. If we know in exact detail the state of the world at one moment, we could calculate, like theoretically at least, the state of the world at every other moment, both in the future and, as it happens, in the past. So, that's the picture of the world that we're working with in this first chapter, and then later on we might be adding other physical theories to make things more complicated. What, Albert asks, is time reversal invariance? And how can we see that Newtonian mechanics fits it, that has it, is time reversal invariant? Well, Albert says, suppose that you have some physical process in front of you, right? Something that happens over time. So maybe there's a particle that is first here and then there and then there, right? And let's say that it moves smoothly, so it looks more like a Newtonian particle. That's what the particle is doing. So it's here, there, at sort of infinitely many points of time. It is at infinitely many different positions. What would it be for that process to happen backwards? Well, Albert says, what that would be is you take the state of the world at each of these moments and then you put them in the reverse order. Right? So rather than a particle being here, then here, then here, then here, etc., you look at a particle that has the same states but in the reverse order. So it's here, then here, then here, then here, and so on. Right? And so, of course, what it's going to look like is a particle moving in the other direction. And that seems fair, right? That seems like a really great description of what the time reverse, like the opposite in time of the first process, looks like. But, Albert says, it is extremely important to be clear about what exactly belongs to the state of the particle at a particular instance. The way I just described it, the only thing that belongs to the state of the particle is its position. It's here, then here, then here, then here, then here, and if we reverse that, then it's here, then here, then here, then here. Right? I'm just talking about positions. Now suppose that we also talk about velocities. So suppose that we say, well, the state of the particle at a particular moment is that it has a particular position and a particular velocity. So first it's here with a velocity in that direction, right? That direction. Here with a velocity in that direction. Here with a velocity in that direction. Well, if I take those states and I put them in the reverse order, I have a particle that is here with a velocity in that direction, a particle that's here with a velocity in that direction, a particle that's here with a velocity in that direction. And so what I'm seeing is a particle that is moving that way, but has a velocity in the other direction. That doesn't make any sense, right? It doesn't make any sense to think of a particle moving in one way while at the same time having a velocity in the other direction, in the opposite direction. That doesn't make any sense. So in order to make sense of this, I can do two things, right? In order to talk about this as a time-reversed process, in order for it to even make sense of it to think as a time-reversed process, I either look at the positions alone and just not at the velocities, or I look at the velocities, but I have to flip the velocities around, right? And so I say that the time reverse is not just taking the states and putting them in the opposite order, it's taking the states, flipping the velocities in all of those states, and then putting them in the opposite order. I have to do either of those two things. And Albert in the book says that the right thing to do is clearly the first thing. Right? The only thing that belongs to the state of a particle at a particular moment is its position and not its velocity. And Albert's argument for that is that he thinks that the instantaneous states of the universe have to be logically independent of each other. So there's a state now, and there's a state at other moments of time, and they have to be completely independent. Anything, at least logically speaking, could happen after anything else. And if velocities were part of the instantaneous state of the universe, then that wouldn't be true. Because if there's a particle here with a velocity in that direction, then a little bit afterwards, maybe infinitesimally so to speak, like if you look at the time derivative, to say it more mathematically and technically, of its position, well, it's got to be moving in the direction in which it has velocity, right? And so the velocity at a particular moment tells you something about the positions at other moments. And so if velocities are part of the state of the world at one moment, then the states of the world at different moments are not logically independent of each other, but they are logically dependent on each other. Now, if you believe, as Albert does, that they can't be, that every moment of the world has to be sort of its own thing, you have to be able to combine different different states of the world in any which way, at least logically speaking, then clearly Albert's choice is the right one. You just take the positions and you leave out the velocities. I don't think Albert gives us any sort of reasons to believe that instantaneous states of the world have to be logically independent of each other. I think he is sort of committing himself to a sort of Humean picture of the world where, well, that is precisely what's going on. Anything can come after or before anything else. And there are alternative ways of thinking about the world that disagree with that. I myself have very recently published an article called Presentist Velocities, where I precisely suggest that we do need velocities at instantaneous moments, and where actually for me it is a good thing that different moments in the world are not logically independent of each other. So I don't think that Albert tells us why exactly we have to follow his way of doing things rather than the opposite way of doing things. But maybe it's also not too important, right? The important thing is to be aware that if you add more to the state of a system at a particular moment than only its positions, then you are going to have to think long and hard about what you mean by the time reverse. And if you add velocities, then in order to make any sense at all of things, you are going to have to flip the velocities around when you make a time reverse of the process. Okay. This is going to be extra important as you move beyond Newtonian mechanics. But we'll get to that in a second. So, now, let's take Newtonian mechanics. Here's what makes a time reversal invariant. If any process fits the laws of Newtonian mechanics, then the time reverse of that process, either the way that Albert defines it as just the positions in the opposite, let's say, ordered in the opposite direction, or in the way that I would prefer to define it, where we also flip the velocities. It doesn't matter, you get the same process. That time reversed process is also going to fit the Newtonian laws of motion. So if you make a video of some particles moving according to Newton's laws of motion, and you reverse the movie in the way we just described, they are still going to be obeying Newton's laws of motion. And that may sound a little bit weird, right? I mean, you might think, well, but there are all these asymmetric things in the world. Like an apple, it can fall from a tree, and then it bumps on the ground, and it rolls a little bit, and it lies still. But apples don't jump up from the ground and reattach themselves to a tree. And yet, if you were to look at a movie of that at the level of Newtonian particles, you would see something that is totally okay with the laws. What you would see is a lot of movement of particles in the ground coming towards the apple at the same moment, and all of these particles sort of from the ground bumping into the apple right at the same moment, launching it upwards towards the tree to exactly where the stem is waiting, bloop, and there it is. And that's weird, and we don't expect to see that in reality, but it seems to fit Newton's laws of motion just fine. That's the mystery, right? That's what we want to explain later on in the book. Okay, so it seems to fit Newton's laws of motion just fine. And in fact, you can also mathematically see fairly easily that Newton's laws of motion are going to be time symmetric, because where does time enter in? Well, really, it enters in only in this law, F is m times a. And what is a? A is the second time derivative of the position. So the position, like how it changes over time, is the velocity, and how the velocity changes over time is the acceleration, it's the a. And so what you're going to see in that formula is t squared, right? T squared, the time squared. And so if you change t for minus t, well, 4 squared is 16 and minus 4 squared is also 16, right? The two minuses are going to cancel out. So it's actually fairly easy to see that this Newtonian law of motion, where time only appears squared, is going to be completely the same if you reverse the direction of time and change t for minus t. So that's what we can say about Newton's laws. What about other physical theories? Well, first of all, there seems to be one part of physics that is really time asymmetric, and it has to do with the decay of a particular kind of particle, and nobody knows what it has to do with apples or eggs or aging or whatever. So Albert says, I'm going to set that aside for now, and I'll set it aside for now too. So we're going to ignore that. When we think about sort of the main later theories that there are, let's say something like electrodynamics, which adds to Newtonian mechanics, electrical fields and magnetic fields and so on, is that time reversal invariant? Well, Albert says no. No, if you take these like positions of the particles and the electric and magnetic fields and so on, and you reverse the order, then you're actually going to see things that don't work, that don't fit the laws. In order to make them fit the laws, you would have to do something more than just put them in a different direction. You would also have to flip around all the magnetic fields. And so he thinks that technically speaking, these laws are not time reversal invariant. And given his definition of time reversal invariance, he is of course right. But if you had already taken the second strategy, where you say, oh, you know, our state descriptions are somewhat rich, they also involve velocities. In order to get the time reverse of something, we need to flip velocities. Then you might think a little bit more and come to the conclusion that you also need to flip magnetic fields and who knows what else in other theories. And so I don't think, Albert doesn't like it, he doesn't think it's very clean or clear, and that's right, it's not as clean or clear as his approach. On the other hand, it's possible, and it is going to get you the same sort of philosophical result as the one that Albert gets. Because what Albert says is that although all of these other later theories are not time reversal invariant in his sense of the word, they are time reversal invariant if we look only at the positions of particles. So if we only look at the positions of particles and we reverse time, then we're gonna see something that fits the laws. How does it fit the law? Well, we would have to choose the electric and magnetic fields in a particular way. Namely, we would have to choose them in such a way that the magnetic fields are flipped around. And so we basically have to do the same kind of operation. Now, not to see that the laws are time reversal invariant, but to see that at least they are time reversal invariant insofar as only the positions of particles are concerned. And it comes to more or less the same thing. Right? So what we can say is that the laws of nature as we have them by themselves just really do not seem to be able to explain that there is so much asymmetry in how things move around in the world. Right? That is the important lesson that we learn from chapter 1. The laws of nature as we have them in a whole sequence of physical theories just do not seem to be able to explain, at least on their own, if we don't add something to them, they don't seem to be able to explain why the world is so asymmetric and the past and the future seem to be such different directions. In order to answer those questions, we're going to have to delve more deeply into physics, and in particular, Albert is going to take us onto a tour of thermodynamics first, then statistical mechanics, then he's going to try to think through whether those parts of physics, and especially thinking about something like entropy, helps us explain time asymmetry. That's going to turn out to be very complicated. He is going to bring in some cosmology with what he calls the past hypothesis, but that's for later on. For now, what we've seen is, well, we've thought about time reversal invariance, and we thought about the laws of nature and how they are unable to explain the asymmetries in the world around us.